we shall now see how do we establish the position and the nature of the side chain on cholesterol. Now we have a side chain over here. We need to establish that it is present on carbon 17, and also we need to establish that it is a 7 carbon chain. 1, 2, 3, 4, 5, 6, 7, 8 carbon chain. Alright, now we'll see that. Now this establishment of the position of the side chain and nature of the side chain, we can divide it into two. Let's first discuss the position of the side chain. To know the position of the side chain, the following reaction has been done. Cholesterol has been acetylated. That is done in order to protect the OH group. So this OH group has become acetate group. So you get cholesterol acetate, which in oxidation gives a steam volatile compound and acetate of hydroxyketone. Now, in the acetate of hydroxyketone, the keto group was present over here on carbon 17. So that implies that the point of attachment of the steam volatile compound to the cholesterol nucleus must be on carbon 17 through the keto group. So this the position of the side chain must be on carbon 17, we can say. And the side chain must be an 8-membered chain because it has a structure similar to isohexyl methyl ketone. Okay, so this steam volatile compound had a structure similar to isohexyl methyl ketone. Now we need to establish that this steam volatile compound has similar structure. Alright, so now we have established that the position of the side chain is on carbon 17. This also, point is also proved by the selenium distillation. You get Diels hydrocarbon. Okay, so you can refer back to that particular point also, and you can add that to this. Alright, now let us look at the how do we establish the nature of the side chain. Now to establish the nature of the side chain, we are going to use a degradative method called Barbier-Wieland degradation. Now Barbier-Wieland degradation is shortening of the carbon chain of carboxylic acid group by 1 carbon. So if you have a carboxylic acid group, a long chain carboxylic acid group, you can shorten the carboxylic acid chain 1 carbon at a time, provided the carboxylic acid group has a methylene group attached to the methylene group present adjacent to the COOH group. Say for example, you have a COOH group here, carboxyl group, and you have a methylene group. So this must be the system. So that means you must have a CH2COOH group. If such a structure is present, then you can carry out Barbier-Wieland degradation. And during that degradation, 1 carbon is lost from the carboxyl group. So the method of Barbier-Wieland degradation is first you have to treat the acid with the Grignard reagent. So Grignard nucleophilic addition and hydration happens, and you get onto the carboxyl carbonyl, the phenyl group of the Grignard reagent gets attached. Okay, and then the next step is dehydration reaction, removal of H2O, and that happens, and intramolecular dehydration happens, and you get a double bond on this. The next step in Barbier-Wieland degradation is oxidation, wherein the double bond breaks and you get a ketone in the carboxylic group. Okay, so the carbon which is having a hydrogen attached to it will form the carboxylic acid compound, and the other carbon will form the keto group compound. So here you can see this carbon, that is to which R is attached, has a hydrogen also. So this particular system becomes the carboxylic acid group. You can see here, and the fully substituted carbon becomes the keto group. So this is Barbier-Wieland degradation. Okay, we are not going in detail into the mechanism that you will be studying elsewhere. Okay, so just understand that in Barbier-Wieland degradation, the carboxylic acid chain having methylene group adjacent to COOH can be broken down one carbon at a time. Now this can be used to understand the number of carbon atoms in a hydrocarbon chain or in an organic compound by successively removing one carbon at a time. So we can see up to what extent the number of carbons can be removed. Now let us take up this particular method for understanding the structure of our side chain in cholesterol. So in order to carry out the Barbier-Wieland degradation, first we have to convert our cholesterol to cholestein. Okay, so this we have already done earlier also, reducing cholesterol to cholestanol, oxidizing that to cholestanone, and then reducing it to cholestein. Now you get a hydrocarbon C27H48. Now this cholestein is then subjected to Barbier-Wieland degradation. Now let us see step by step how this is done. Now the 5-beta cholestein, the C27H48 compound, which we have got after reduction, and this cholestein is then oxidized to get acetone and 5-beta cholanic acid. Okay, so you have acetic acetone, 5-beta cholanic acid is formed. Now formation of acetone indicates that the side chain terminates in isopropyl group. So you must have an isopropyl group on the end of the side chain. That's why you got acetone on oxidation. Okay, now the 5-beta cholanic acid is a C24 chain. Now what you get is a C24 compound because 3 carbon has been lost as acetone. Now this C24 compound, 5-beta cholanic acid, is subjected to Barbier-Wieland degradation. You get C23 compound, nor 5-beta cholanic acid. So we have lost one carbon atom here when we move from 5-beta cholanic acid to nor 5-beta cholanic acid. In the next Barbier-Wieland degradation, again one more carbon is lost. You get bis-nor 5-beta cholanic acid, which is a C22 compound. It has got 22 carbon atoms here. This bis-nor 5-beta cholanic acid is again subjected to Barbier-Wieland degradation. We lose one more carbon atom and you get etiocholyl methyl ketone. Okay, you get etiocholyl methyl ketone, a 21 carbon compound. Now formation of this etiocholyl methyl ketone or this ketone indicates that an alkyl group is present on the alpha carbon of bis-nor 5-beta cholanic acid. If alkyl group was not present, then we would have got an acid compound instead of ketone. Okay, so we would not have got etiocholyl methyl ketone. Instead of ketone, we would have got an acid. Okay, so that indicates there is a methyl group attached to the alpha carbon of bis-nor 5-beta cholanic acid. Okay, so that a chain terminates at as isopropyl group. Then we are losing 1, 2, 3 carbon atoms. Okay, so there is 3 carbon atoms attached to this isopropyl chain group. You can imagine that. Also, there is a methyl group attached to the alpha carbon. Alright, now this etiocholyl methyl ketone on further oxidation gives you 5-beta etianic acid, which is a C20 compound. One more carbon is lost there. When we go from etiocholyl methyl ketone to 5-beta etianic acid, we are moving from C21 to C20. Okay, so now this formation of 5-beta etianic acid indicates that the ketone must be a methyl ketone, and hence the alkyl group on alpha carbon of bis-nor 5-beta cholanic acid is a methyl group. Okay, so the alkyl group attached to the alpha carbon on bis-nor 5-beta cholanic acid is a methyl group. Alright, so this from when we came from cholesterol, 5-beta cholesterol to 5-beta ethanic acid, we have lost 7 carbon atoms. Okay, that we must keep in mind. So from C27 we have reached C20. So the side chain must have at least 7 carbon atoms. So that is or 7 or more carbon atoms. We have to decide to that. In ethanic acid, the carboxyl group is attached directly to the nucleus. That's been proved. Okay, so as we have said earlier, from 5-beta cholesterol to 5-beta ethanic acid, there is a loss of 7 carbon atoms. So probably the structure of the side chain must be something like this. Okay, and now you have the isopropyl terminal end. We have a methyl group on the alpha carbon. Now let us see how this the steps we have taken up earlier, just now, will fit into this structure. Let us see that. So initially we started with cholesterol, that is a 27 carbon atom compound, and then we carried out oxidation, and we got 5-beta cholanic acid and acetone. So this must be the acetone moiety, or isopropyl group is lost, and you get C24. Okay, now we are going to do Barbier-Wieland degradation. So this carbon is lost. So one Barbier-Wieland degradation is over. You get not 5-beta cholanic acid, C23 compound. Then another Barbier-Wieland degradation. This carbon is lost. Bisnor 5-beta cholanic acid, a C22 compound. And one more Barbier-Wieland degradation. You get etiocholyl methyl ketone. So the keto group will be formed here. Okay, so if you have a methyl group, methylene group, then you get acid, but you don't have a methylene group here. You have a hydrogen over here and a methyl group, so you get etiocholyl methyl ketone. Okay, so we have done 3 Barbier-Wieland degradation, and now we are going to oxidize this etiocholyl methyl ketone. When we oxidize, this methyl group undergoes, this side chain undergoes oxidation. You get 5-beta ethanic acid. So this carbon will get converted to COOH. So the COOH is directly attached to the R group, or the nucleus of the cholesterol. So the set of reactions we have done fits into the structure, or you can say the structure of the side chain fits into the series of reactions we have carried out to elucidate its structure. So we have seen that the position of the side chain will be on carbon 17, and the side chain nature of the side chain will be like this. Okay, hope it's clear to you. If you have any clarifications, please feel free to ask. Thank you.